Now we move into the heart of multi-phase reservoir flow, effective and relative permeability. If absolute permeability tells us how easily a single fluid flows, relative permeability tells us how fluids compete when oil and water, or gas and oil, flow together. Absolute permeability is measured when a single fluid fully saturates the rock. It describes the rock's baseline flow capacity. However, reservoirs almost never flow as single-phase systems during production. So absolute permeability is only the starting point. Effective permeability is the permeability to a particular phase when other phases are present. For example, oil effective permeability depends on water saturation. The key idea is that the presence of another fluid reduces the available pore space and flow paths for a given phase. This slide to emphasize how effective permeability changes with saturation. As water saturation increases, oil effective permeability decreases. This is why production often declines as water cut increases. The rock becomes less conductive to oil. Relative permeability is effective permeability divided by absolute permeability. It is a dimensionless function that tells us how available the rock is to each phase at a given saturation. Relative permeability curves are essential inputs to reservoir simulation and to predicting water breakthrough and recovery behavior. This slide typically shows that at irreducible water saturation, water relative permeability is near zero and oil relative permeability is high. ASSW increases, KRW rises and CRO falls. At residual oil saturation, CRO approaches zero. Teaching point. These endpoints determine key recovery limits in water flooding and gas displacement. Use this slide to reinforce interpretation. The shape of KR curves depends on pore structure, wettability, and rock type. Two rocks with similar absolute permeability can still have very different relative permeability behavior, leading to very different recovery performance. Relative permeability is influenced by wettability, pore geometry, saturation history, interfacial tension, viscosity ratio, clay content, and heterogeneity. This is why relative permeability is often measured in SCAL programs rather than assumed. Teaching message: KR curves are not universal. They must be rock and fluid specific. This slide usually emphasizes endpoints, SWR, SOR, curve shapes, hysteresis, and the fact that relative permeability functions represent multiphase competition in the pore network. A practical teaching point: if you change wettability from water wet to oil wet, the whole KR behavior can shift, affecting recovery significantly. Relative permeability functions are used in water flood design, forecasting water cut and oil rate decline, estimating recovery efficiency, reservoir simulation and history matching, evaluating EOR methods where saturation paths change. In short, relative permeability is one of the most important dynamic rock fluid inputs to every reservoir forecast. This slide reinforces that KR curves are direct inputs to simulation models. If KR curves are wrong, simulation predictions can be wrong even if porosity and permeability are correct. This is why SCAL is often a high-value investment in reservoir studies. This slide introduces the steady-state method for measuring relative permeability. The core idea is to inject oil and water at controlled rates until steady state is reached, meaning production rates and pressure drops stabilize, then compute effective permeabilities and convert them into relative permeabilities. This requires careful saturation measurement and careful control of experimental conditions. This slide explains hysteresis. During drainage, the wetting phase stops flowing at irreducible wetting saturation, defining maximum non-wetting saturation. During imbibition, the non-wetting phase becomes discontinuous and stops flowing at residual non-wetting saturation. This is why accumulation and water flooding follow different KR paths. Practical message: reservoir history matters, and hysteresis is critical in cyclic processes like gas storage or repeated injection/withdrawal. The basic workflow in a water-wet oil-water experiment is inject oil and water at constant rates until steady state, measure stable production rates and pressure drop, determine saturation in the core, usually by resistivity or weighing, change injection ratio and repeat. Explain the key lesson. The saturation inside the core is not necessarily equal to the injection ratio. The pore network and wettability control how fluids distribute. Let's summarize the essential takeaways. If fluid saturation is the fraction of pore volume occupied by each fluid, saturation can be measured directly from core or inferred from capillary pressure and logs. Relative permeability describes how multiphase flow reduces flow capacity for each fluid. Relative permeability is measured in SCAL programs, commonly by steady-state experiments. Capillary pressure controls transition zones in fluid distribution. Capillary pressure and relative permeability are critical inputs for reservoir simulation and recovery design. If you can explain these 6 points clearly, you have the core of this week. Thank you very much for joining this week's lecture on fluid properties. This week we connected lab PDT concepts, fluid saturations, capillary pressure physics, and relative permeability functions, the core building blocks of multiphase reservoir behavior. These concepts are central not only for petroleum production, but also for CO2 storage, groundwater flow, and other subsurface engineering applications. If you have any questions, please ask, and in the next lecture, We will continue toward reservoir modeling.